Hello, am I audible?
Yes, yes.
Okay. So I hope my screen is visible to you all.
Yeah, it's visible.
Okay, fine. So I think we are good to start. It's time is over. So let's start. So good evening, everyone. Um, Today we entered into the week 8 of doubt and problem solving session of in the course of techniques of material characterization. And this week we will be mainly cover the type of question which will help to solve your assignment number 8. So I hope that you have gone through the lectures of week 8, and there you had an understanding of regarding a different kind of a detector, like your ADS detector, how it works, what are the principle, and what can we found out from the EDS and the WDS, as well as in this week there are some imaging and the contrast formation was also there for the to capture the topography image by using your secondary electron as well as the backscattered electron. So in this way, this week has some a lot of information which will be helpful to understand in a more deeper and efficient manner of scanning electron microscopy. So let's begin with our assignments question that will, I mean, our practice question that will help in your assignments. So we will discuss regarding that. Okay, so first question is a very basic question, and it is a fact that we can know, and in the lecture is all in lectures also sir has explained. So the question is, the window which prevent the contaminants from a specimen chamber in EDS detector is made of what material? So here actually what happened, there is a specimen chamber in the in SCM. So there is a EDS detector. If you have seen the basic setup and how it looks, where the detector has placed, so you will have an idea that there could be possibilities of many contaminants from the specimen chamber that can attach to the detector. That will give some not very good result in detection. So that's why we don't want contaminants in that detector. So what could be that material? Beryllium or carbon, beryllium or aluminium, carbon or aluminium, and the last is aluminum or zinc. So, what could be according to you? Anyone?
Option B.
Option
I think
B.
it's B.
Okay, you are saying that beryllium or aluminium, right?
Yes, sir.
Yes, yes.
Okay, fine. So let's see, and what are the correct option? I think you're almost right, but not very accurate, I can say. So, okay, I will explain this. So, as you can see, this is the setup you can also see in your lecture. So there is a PN junction. Okay, so this is your silicon. Okay, so silicon semiconductor junction, the I region occupies most of the, so this will be the thick, and there will be the your P junction and your N. Okay, and this is your window. So this is your beryllium window. So actually the gold coated outer surface is usually further protected. So there will be the gold coated outer surface will be there in your EDS, and that is further protected by a thin window, a very thin layer of your beryllium or a polymer. So actually beryllium is having a less atomic number, so also sometimes we use beryllium or carbon, not aluminum, because aluminum is having a high atomic number. So the correct answer will be your beryllium and carbon. So actually what happened, this window is used to protect from the contaminants, the to the EDS detector inside the environment chamber of the microscope, and from condensing on the very cold surface of the detector. So it also forms a further barrier to the entry of your X-rays. So here, the thin film of gold on the outer surface of the detector must be as thin. It should not be very thick, as thin as possible, so that a very few X-ray are absorbed in it, and not all the only very few X-rays are absorbed in it. A layer, it is very thin. You can say roughly around 20 to 25 nanometer thick. So that will provide a adequate conductivity. And on top of this gold coated outer surface, we have a thin window of beryllium or carbon or polymer. So the window, despite being made of beryllium, so beryllium is having atomic number of 4, or carbon, you can see here beryllium is having atomic number of 4 and the carbon is 6, the only being a few micrometers thick. This, the range of this thickness should also, you should remember that it is in the range of micrometer, absorb a significant proportion of the low energy X-rays falling on the detector. So there is X-rays are falling on the detector. So this because it has a few micrometers, so that this will absorb the significant proportion of the X-rays, so therefore makes light elements particularly difficult to detect. So this is the reason. So here you can see the, here the window which can prevent from the contaminants from a specimen chamber in the EDS detector will be your beryllium or carbon. Okay, so the right answer will be your beryllium or carbon, because it has a low atomic number. So which of the following element cannot be detected by EDS? So this is very simple. If you have gone through the EDS analysis of your sample, then probably they have some limitations, then you might able to answer this question. So can you give your answer for this? The silver, aluminum, titanium, and boron.
Is it D, boron?
Okay. Anyone else wanted to give any answer? Anyone? They have some different opinion. I have just said regarding some, just think regarding in the line of your atomic number. So you will be probably answer this question. This is related to atomic number. Okay, let's see. So this is the slide. This you can simply find. So what is the limitation of your EDS detector? So here you can see in the last point, EDS cannot detect the lightest element. Okay, typically below the atomic number of sodium. So what is the atomic number of sodium is 11. So the elements which has atomic number less than 11 for detectors equipped with a beryllium window. So we have seen that we are using a beryllium or carbon. So the which is equipped with the beryllium window. So here we can't detect the element which has a atomic number lower than the 11. Polymer based thin windows allowed for the detection of a light elements depending on the instrument and operating condition. So here in the last to last slide we have seen that there is also possibilities of a thin window of beryllium or a polymer. So but most of the ADS detector is equipped with a beryllium window. So that's why we can't go for the lightest element. We can't detect the through by using your EDS. Okay, and here also some limitations are like there are energy peaks overlap among different elements, particularly those corresponding to X-ray generated by emission from different energy level, like your K cell, M cell, L cell, in different elements. For example, there are close overlap of if suppose there is a overlap of manganese K alpha and chromium K beta or titanium K alpha and various L lines in your this BA, particularly at higher energies, individual peaks may corresponding to several different elements. In this case, the user can apply deconvolution method to try peak separation. So it is saying about that there are sometimes the overlapping of the your peaks, so that you have to there is a many way that you can separate this kind of a peak also. So these are some limitations, and in strength also the EDS can be used in a semi-quantitative method to determine chemical composition by peak height ratio relative to a standard. Yeah, so this is here suppose if you have any sample metallic, suppose you have a multi-phase sample, there you have a suppose it is a alloy of a different aluminum, suppose you have a titanium, aluminum, vanadium, and you have to determine that what is the composition of your titanium, what is the composition of your aluminum, what is the composition of your vanadium. In that case, if you will do this your EDS analysis, EDS analysis, then that will show your chemical composition by the peak height ratio relative to a standard. So in this way, we use our EDS to detect the chemical composition of our sample. But here is the limitation: we can't detect if your sample suppose is having a let's say your carbon. Okay, so carbon is there. So or you can say what is the mm, uh, suppose if you have some hydrogen or something very lighter, okay, suppose it has a boron, so it can't detect those elements because it is lighter elements. So the answer will be the D, boron we can't detect by EDS. In EDS detector, the resistivity of silicon is increased by what? Okay, so as we have seen in the I think first or second slide, I have shown you that the silicon in between the PN junction. So what how can we increase the resistivity of your silicon? So first one is you're keeping the PIN. Okay, so A is you're keeping the PIN junction in reverse bias, doping the silicon with lithium, cooling the whole detector to 77 Kelvin, or with all of the above. So if you have seen or if you have some knowledge, maybe probably you might be able to answer this question. So can anybody guess this?
The answer is D, all the above.
All the above. Okay. Okay. Anybody else? They have some. If you have some different answer, or if you have, uh, if you would like to give some comment on this, think. No. So I think somebody has said all of above, and which is right. So here in this slide, so this is basically a SCM setup. If you have seen, and here this is the screen where you can see your images, and there is another PC where you can use for your EDS. There you can see your composition. So here it is saying in the red red statement, you can see that the resistivity of silicon is increased by, there are how many? Three types. Okay, so first thing is making the whole detector a semiconductor PIN junction, which is reverse bias. So by making it the reverse bias, we can increase the So for this, how what is the reverse bias and how can we make the this PN junction? If you have forgot, then read any basic or physics or the basic this electronics book where your is I mean 11 12th grade the P about your PN junction and what is the reverse bias, forward bias. So there you will have an idea of basic idea that and what is the resistivity, there is what is the difference between the resistivity and the resistance. So these are some basic physics questions. So I will because we have a lot of questions, but here I can give you the answer that the making the whole detector reverse bias. And second thing is doping. Okay, so there is a silicon, I will also show that slide again. And okay, so and we can dope the silicon with a small concentration of your lithium. And the third one is cooling the whole detector to liquid nitrogen temperature, so 77 Kelvin. So think this 77 Kelvin, 273, it means your 0 degree. So so, what is your 77 Kelvin means what? The liquid nitrogen. If you have seen the liquid nitrogen, then you might able to, liquid. It means in degree Celsius, it would be around 196 or 195 around degree centigrade. Okay. So, if you will cool the whole detector to the 196 degree centigrade, then the resistivity can be increased. Because for this you have to understand why this is happening. Then you can probably read some book where you will show that what is the effect of the temperature on the resistivity of your silicon. Okay, so these are, there are some basic physics behind this kind of a logical question. So these are saying three statements. So yeah, so PIN junction which I have showed in this is the PIN junction. Here this is your silicon. So the second one which shows that this silicon we can, there is a lithium dope. So if you will doped, so here also why the probably if you will know and if you will read the book of any standard book, then what is the effect of doping on silicon, what is happening inside there. Okay, what is exactly happening in the mechanism of your charge transfer, how the electron hole pair are generating and how it is contributing towards the resistivity change. Okay, so these all are the very conceptual question. This is not just a factual kind of that so you will probably able to if you will read about, then you will have a more curiosity that okay, this is happening, the effect of temperature, the effect of doping, and the one is your PIN junction reverse bias. Okay, so these are the three things. And here also the current which normally passes between the electrodes is very small until an X-ray enters the detector, and then the resultant current can be amplified and measured fairly easily. So this is something else. So answer will be your D, all of the above. Okay. So here in EDS, aluminum K alpha X-ray with an energy of 1.49 kilo electron volt will give rise to approximately how many number of electron hole pair. So it is asking that if you will use an X-ray of what? Aluminum K alpha. Okay. And it has an energy of 1.49 kilo electron volt. So how many electron hole pair will be generated? So can you have any guesses or any answer for this? Or what do you think? Anybody?
Is it 392?
392. Okay.
1.49 into 10 power 3 divided by 3.8.
Okay. How did you find it out?
So the energy required for the excitation is 3.8 electron volt, right? So
Okay.
we have 1.49 kilo electron volt. So
Hmm.
1.49 into 10 cube divided by 3.8.
Okay.
Is that right? I don't know.
Okay, fine. So I think the answer which you gave and which is right. So there is a range actually. So here, if you will see or if you will read that how can we get the electron hole pair numbers. So here they have given. Okay, so the energy required for each of this excitation is only 3.8 electron volt. Consequently, the number of electron hole pairs generated is proportional to the energy of the X-ray photon being detected, right? So, for an example, the aluminum K alpha X-ray with an energy of what 1.49 kiloelectron will give rise to approximately 390 electron hole pair. Okay, so you can say this could be in the range of your 390 to 393 or 394. And if a voltage is applied across the semiconductor, current will flow as each X-ray photon is absorbed in the detector, and the magnitude of the electron will be proportional to the energy of incident X-ray. So it is saying that each X-ray photon is absorbing there in the detector, and the magnitude, okay, so the current will be there. So the magnitude of current that is also proportional to the energy. Okay, so the whatever the incident X-ray is coming, it has some energy, and the current will be proportional to that energy, right? And the high efficiency of the EDS detector coupled with a relatively large collection angle. So there is also an effect of your collection angle, typically greater than the zero point 0.5 steradians in SCM, means that the data can be collected rapidly at quite low beam current. Okay, so if you want to collect your data very rapidly with a low beam current, then you have to give some angle, collection angle. So this is saying in steradians, so that is 0.5. So here the answer for this question is here, because here the excitation is only 3.8 electron volt it is requiring, and for the energy is giving 1.49 electron volt, kilo electron volt. So if you will see also in the lectures, so by using this you can be able to generate electron hole pair which is around 392, 392 or 393 or 390 electron hole pairs. Okay, so this is the again the same thing that I have shown you few slides back, and which is, if you remember the with diagram which I shown you 3-4 times. So this is asking about the thickness. So in EDS detector, which of the region has or have the highest thickness in silicon semiconductor junction? So P junction, N junction, I junction, or both P and N, PN junction. So if you remember the diagram, you will be able to answer.
Should say I junction.
I junction. Okay, yeah, which is right, correct. So anybody else is having different answer, or are you will you go with the C?
C.
Okay, fine. So this is again the same. You can see there is a P. This is a gold negative, and there is a positive, and this is your P and N, and this is your I. So PIN. So this is silicon. Okay, so this is asking about what, the highest thickness of silicon semiconductor junction. Okay, so the your I will be your thick. This is around. This is your you can see the hole is your 3 mm. So the silicon semiconductor junction, the I region occupies most of the 3 mm thickness. Okay, so this is 3 mm. So this I region in silicon semiconductor junction, this occupies the most of your 3 mm thickness region. So the answer will be your I junction. Okay, so in WDS techniques, if the spectrometer is placed at a particular drag angle, then it will detect what? So this is regarding that WDS. So this is for your wavelength. So in the characteristics X-ray with a particular value of wavelength, particular value of energy, and second is your the continuous X-ray of particular value of wavelength and continuous X-ray with particular value of energy. So can you give the answer for this?
Is it C, a continuous X-ray with a particular value of wavelength?
Okay. Anybody else having different? If you want to guess or give the answer. Huh. Okay. So somebody said the continuous X-ray with particular value of wave. Okay. So actually in WDS, there is this is for the X radiation coming from the specimen is filtered so that only X-rays of a chosen wavelength. Okay, so there is a filter. So only X-ray of a chosen wavelength, not all the wavelength. Usually the characteristics X-ray wavelength of the element is interest. Okay, so this is usually the not continuous characteristics X-ray wavelength of the element of interest are allowed to fall on a detector. So from here there is a two characteristics X-ray, so either A or B. So since WDS is regarding your, this will only choose the wavelength. So here it is saying not for the energy, only the X-ray of chosen wavelength. Okay, so the it will not allow all the wavelength of your X-rays, so because there is a filter. So X-ray coming from your specimen which will filter further so that it will only allow the X-rays of chosen wavelength. And usually the element of interest will be your the characteristics X-ray wavelength, and that will allow to fall on a detector. Okay, so there is a word filtered. So the filtering is achieved. So here we are filtering of what? Only some wavelength of your X-rays. So filtering is achieved by crystal spectrometer, which employs diffraction to separate the X-ray according to the wavelength. Okay, so this will give you this is spectrometer, crystal spectrometer, that will employ diffraction to separate. So this will give you the X-rays of some particular wavelength so that we can filter by using a crystal spectrometer, and that will only allow the characteristics X-ray wavelength of element of interest. So here the characteristics X-ray with a particular value of wavelength lambda. Okay, so A. The thing next is which I just shown in the image. If you have but I do not uh, uh, give the more focus towards that because I was knowing that the next question will be regarding this. So in order to achieve the focusing effect in WDS, the specimen, crystal and detector must lie all on one circle, which is known as what? So this is very simple. It was written in the last slide also. So please give the answer for this question.
C.
You answered C, roll and circle.
Okay, fine, great. So the answer is correct. So here, this is your Roland circle. The name of the circle is your Roland circle. So what is it is asking? The specimen, crystal and detector. Okay. So this is your specimen and detector. So here it is saying in order to achieve this focusing effect, specimen, crystal and detector must lie on a circle of radius known as Rowland circle. Okay, So since the X-ray detector normally used in a crystal spectrometer capable of counting at very high rates, okay, it may be possible to collect data from a single element in a very short counting time. So it is saying about your timing that you can collect the data for a very short time by using this crystal spectrometer, and because it is capable of counting very high rates. And also this crystal spectrometer is designed in such a way that the geometric efficiency is low and the solid collection angle of 0.1 steradian is typical. So the detector efficiency is also quite low, typically less than 30% because of losses of both diffracting crystal and the counter. So it is saying about that detector efficiency is quite low. So in order that as many as possible X-rays leaving the crystal, okay, so which is living from the crystal, arrives should be arrived at the detector so that we can detect that signals. The geometry of the spectrometer is chosen such that all possible X-rays path are focused onto the detector. So here we want that as much as signals can be detected by your detector. So here this is your specimen and this is your detector, and here it will be your crystal. Okay, so that all your detector and the specimen and your specimen, crystal and detector. Okay, so this is your crystal, this is your detector, this is your specimen. So here if you will see that there will be one circle, so this should fall onto this circle so that we can I mean so that we can maximum signals can arrive at the detector. Okay, so there are some geometrical regarding this. If you will see this lecture, you will have a much better understanding. So the answer will be your Rowland circle. So which of the following statement is correct for the WDS techniques? Only one wavelength of X-ray is detected at one time. Simultaneously, we can detect all X-ray of every element are detected. Scan time of WDS is faster than the EDS. There is no possibility of line broadening in WDS. So if you know some limitations or regarding what are the advantages, you will probably able to answer this question. So can you guys give the answer for this?
Is it A?
Okay. Anybody else? Anyone else wanted to give? You can simply guess. No need to be correct. This is just asking about the statement which is correct for your WDS. So you have probably known that I have explained in the last two slides that regarding their orientation and what it detects. So can you give on the basis of that? Okay. So so as we have seen that there is some disadvantage of your WDS also. So what are that? So there are some obvious disadvantages in using a crystal spectrometer for qualitative analysis. So it is saying that only one wavelength of X-ray is detecting at any time. A scan of all required wavelengths can take a considerable time. Okay, so there will be a spectro. So in the last, I think here somewhere I have shown you that the filtering is achieved by your spectrophotometer, which employs the diffraction to separate X-ray. So actually there is a only chosen wavelength of your X-rays will fall onto a detector, not all. So it will scan, or it will only scan only one wavelength of X-ray is detected. A scan for all the wavelength, or the all the required wavelength will take considerable time, because it is separating that this crystal spectrometer. So that will take a lot of time. Since the spectrometer employs diffraction, there will be not one angle of the crystal at which a certain line is detected, but there will be a several one corresponding to each value of n, and there may be as many as 7 or 8 order of reflection detectable from a major X-ray line on the spectrum contains far more lines than that collected by the EDS detector. Okay, so these are some disadvantage also, and possibility of signal dilution is also. Line broadening will be there. So here you can see, if you have this is the peaks that you will get from your WDS. So this is your basic schematic, that how your system is placed, and this is electron probe is coming on the specimen, and there will be detector, and there will be your crystal. So yeah, so only one wavelength of X-ray is detected at any one time, or at any time. So answer will be A was right, that whoever has answered. So the next is the grayscale value of a pixel in SCM images depend on the number of what? Photoelectron and the BAC backscattered collected by the detector, transmitted electron collected by the detector, secondary and backscattered electron collected by the detector, auxiliary electron and secondary electron collected by the detector. So if you know that in the last slide, I think in the last lecture also I have shown you some slides regarding this, image formation. So this is simply regarding that the grayscale value of a pixel in SCM image, that will depend on something. So do you have any answer for this?
Option
It's
C.
A.
Option C, sir.
And
Yeah.
somebody said something else also, or both are
No,
saying
it's C. C. C.
okay. And anybody else who has something different? No? Okay, so I think let's see, the answer C is right actually. So here, when an image is acquired, the beam scan, okay, so beam is falling onto your specimen, and it is scanning the sample surface pixel by pixel. Okay, so whatever your image is generated, that will be your, if I have shown you in the last slide, there will be raster on CRT, and this is a specimen, so it will scan like your in a raster scan manner, like this, then the second, and then the third, and in the fourth, and so on and so forth. So in each pixel, the signal is collected by detector and translated into a grayscale value. So when the image is falling onto your sample, and the secondary and the backscattered electron is detected by your detector, and that signal will be collected by your detector, and that will translate into your grayscale value. Okay, so this is secondary and backscattered collected by the detector, and this your I mean signal will be further translated into your grayscale value. If images are required in 8-bit, the range of the pixel will vary from a 0 to 255, and if it is in the 16-bit, then your grayscale value of each pixel can vary from 0 to 65535. Okay, so this will be your regarding your secondary and the backscattered electron, so that will further convert into your grayscale value. So the grayscale value of the pixel depends on how many secondary electrons or the backscattered electron are emitted and finally collected by the detector. So the number of your electrons that are emitted and collected by the detector. So on this, your gray value of the pixel is depend on this parameter. So that's why the SC and backscattered electron collected by the detector, which will be give the your grayscale value of a pixel in SEM image. So the higher the grayscale value of the pixel, the brighter the pixel appear in the image. So here you can see a different. This is your uh, topography of from the secondary, from the backscattered. So this is different, you will see. So this is because of the different pixel. So that will be your C. For a given detection system in SEM, there is a minimum detection current required to observe a particular contrast level. Okay, so we want some contrast. So we are during the detection, there will be a minimum detection current that is required. Okay, we want certain level of contrast. So what is that minimum detection current or the minimum current? So this minimum current will increase when the frame scan time decrease, or when the frame scan time increase, or does not depend on the frame scan time, is always constant. So if you have gone through this, there is some derivation is small. So then probably from that relation you will be able to answer. So can you give answer for this?
It's A, increases with the frame scan timing decreases.
Okay, fine. Anybody else? Anybody else? If you know, I will also give you a slight hint that it is very obvious that it will depend on the frame scan time. So the answer will be from A or B. You have to now know that whether it will be inversely or proportional. It will related to inversely or proportionally. Okay, so minimum usable beam current. So the human eye can detect only distinguish 2 points on a CRT digital display is there will be delta S will be a uh, greater than 5n. Okay, so the minimum level of contrast which can be observed by human eye is given by your this natural that is called your natural contrast, which is given by this C. So here the mean number of electron detected for each pixel, that is n bar, can be related to the operating condition of your microscope, with the beam current will be your I and the frame scan time will be your F. Okay, so we will see in this slide. So here you will have a small derivation. So here if you will go to this red last uh, derivation. So there they have calculated the critical current is required to discern a contrast level C in the specimen, assuming there will be electron charge, which is 1.6 into 10 is to power minus 6 coulomb. So IC will be coming to your 4.2 into 10 is to power minus 12 upon QF and C square. So C square is your what? This will be your contrast level, and IC will be your beam current, and F will be your frame scan time. So it is asking about the minimum. So in order to be minimum IC, your F should be higher. Okay, so F should be your higher. So increase, so minimum current will increase when the frame scan time decrease. Okay, so when the frame time scan this will decrease, IC will increase. So it is inversely proportional. So yeah, somebody has answered A, which is absolutely correct. The backscattered electron efficiency and secondary electron efficiency always minimum when specimen is parallel to electron beam, perpendicular to electron beam, 45-degree tilted to electron beam, or 60-degree. So there is a parallel, it means 0, perpendicular, it means 90, 45, and 60. So what could be your thought on this? Can you give the answer for this?
Answer is B.
B. Okay. Uh, Anyone else? Anyone else and wanted to guess this? There are many people, but yeah, okay. So here, the backscattered electron coefficient is given by your eta, and the secondary electron coefficient is given by your delta, are both a minimum when the surface of specimen is perpendicular to your electron beam. Okay, so this is your tilting angle. So here the angle is increasing. So, okay, and the electron coefficient, this is okay. So here the backscattered eta and the electron are both a minimum when the surface of the specimen is perpendicular to the electron beam. So here the secondary electron coefficient varies with the tilt of the specimen. So here this is given by your del equals to del naught sec theta. So more secondary electrons are produced from the tilted regions of your specimen. Okay, so here when I think somebody has guessed it correctly or they answered it correctly, that the backscattered electron and the secondary are always minimum when the specimen is perpendicular to your electron beam. So we can produce 3D topography images in SEM using what? So this is regarding your 3D, not 2D. SE, BSC, characteristics, both SE and BSC. What is the answer for this?
Is it D?
Okay. Yeah, that is correct. So, as the efficiency of your this is ET detector is not very sensitive to the trajectories of the secondary electron, the number of detected secondary electron increases with the surface tilt. Okay. So here it is partly for this reason that specimen is being studied for topographic contrast are usually tilted with some 20 to 40 degrees towards the detector. Here you can see. Okay, this specimen is your tilted. The incident electron beam is coming, interacting with your sample, and the secondary electron and the backscattered electron is generated. That we have seen in our last session of your. There are some different secondary electron 1, 2, 3, and the backscattered electron, and how it is getting detected by your ET detector. Okay, so here you can see a topographic image. So from your SC and BSC is can be generated by the both. I mean your SC and the BSC. So here you can see the topographic image may also be obtained using backscattered electron, not just by using this is topographic image with your secondary electron in SEM. So here you can see the fracture surface. So this topographic image is generated by using your secondary electron in SEM, and this topographic image is generated by your backscattered electron. So we can say both by using a secondary and the backscattered, we can generate a topographic image. So here the yield of your BSC electron will also increase with increasing the tilt angle, but the direction of the electrons becomes progressively more peaked in the forward direction. So this is also regarding the yield can be increased by your increasing the tilting angle. Okay, so here you can see the beam is directly coming. Here it is at some angle. Here it is also at some more angle. So in this way, if you will see this, watch this lecture, you will have a more clear idea that how the angle can affect your signals, how can we get a better topography of your image. So yeah, by using both secondary as well as the backscatter, we can get a topographic image of your specimen. So to produce the 3D topography in SEM images, we need to produce two images. We need to produce two images in exact identical condition, except the specimen is tilted by a few degree, or except increasing the probe current, and none of the above. So what is the answer for this question?
Answer is B.
B. Okay. So here, when you will tilt your specimen, the electrons are increasingly likely, and that will be more likely to scatter out of the specimen rather than further into the specimen. Okay, so that will be B will be correct. The identical conditions except the specimen is tilted by few degree. So when you will tilt your specimen, that we so in the last slide also I have shown you that you can get a 3D topographic image in SCM. So we need to produce two images, then in identical condition except the specimen is tilted by few degree, you can produce a two images. Okay, so here you can see D at spacing of 45 degree, and this is at 0 degree. So in this way you can get how can you get a more clear topographic image. So BSC signal from the specimen is capable of yielding information about what? So this is just what information can you get from your BSC signal? Only surface topography, composition, both topography and composition, or the electronic structure. So what could be the answer for this?
C.
Okay. So yeah, that is correct. The compositional images also we can get. So here you can see the BSC signals from the specimen is capable of yielding information. Not only just I have shown you in the last slide about the surface topography, but also about the composition. The secondary electron coefficient does not depend very much on the composition. So from the secondary electron, you cannot expect regarding some information of your composition of your sample, although it may be very sensitive to the surface condition and the electronic structure of the material. Okay, so here you can get some idea of your electronic structure as well as some topographic and topographic information. Okay, but by using your backscattered, you can expect information regarding the surface topography as well as your composition. And that this backscatter coefficient, which is given by this eta, varies monotonically with atomic numbers. Okay, so almost independent of your accelerating voltage. So it depends on your Z, and it is independent of your accelerating voltage, because in SCM we applied the voltage also. So the backscatter coefficient from a compound or phase containing several elements may be obtained by using a rule of mixture based on weight fraction. So this is your phase. How can you determine? So this is your W. So this is your weight fraction of A, and NB, it means the weight fraction of 1 minus weight fraction. So although there may be small dependence on down, I mean your this the backscatter coefficient or your density. But yeah, you can get the topography as well as your composition. So the specimen for compositional imaging using BSC mode should be polished flat and unedged, polished flat and edged, unpolished but edged, unpolished and unedged. So here it is saying that a specimen for compositional imaging should therefore preferably be polished, flat and unedged. Okay, because there is a relatively weak of contrast compared to topographic contrast, which may approach 100%. So here it is saying that the contrast from adjacent element is quite small, typically 1 to 5%. That contrast from different phases in an alloy may be even less. So this is giving regarding some how can you, by wearing this, your this is your phase 1, phase 2, and this is giving atomic number of your two different, and this is your efficiency, and this is your difference in contrast. So a specimen for compositional imaging. Okay, you want to be a compositional image, then it should be preferable. Do not etch your sample, and it should be completely flat so that you can get the compositional imaging. Okay, compositional imaging, it means to say you will get an idea that what is the composition of your image, and that will come in the form of your image. Okay, there is your some particular element are there. If you have done the EDS elemental mapping, then you will probably be able to understand this, or you can just simply search in Google. So yeah, these are some questions from my side that we tried to answer, and probably it will be going to help in your assignment solve. So do you have guys any other question?
I have a quick question.
Okay,
So right now we have said that for the composition analysis, the specimen should be unaged, flat, and polished. And for the
okay,
topography, it should be flat, polished, and etched, right?
yeah, 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 yes.
So is it necessary that it has to be polished for the topography?
Polished,
Or
yeah, actually the thing is, for any sample preparation for your optical imaging, whether it could be your optical or the SCM, your surface should be, flat. So if you have a something like your surface is rough, then you won't able to get a proper focus. So that should be very well polished in order to get a better image, right? So yeah, it should be well polished. Okay, that's why we do a multiple polishing of different grades of your emery paper. At last sometime we do our cloth polishing or the diamond polishing. So yeah, polishing, I mean, it is very important to for your sample preparation in order to get a good image. Because if there will be, some roughness, then your image will, in your image itself, you will get some um, not get a good image. There will be some roughness and some cracks kind of a thing, some line. So yeah, it should be flat and polished.
and one
And
more clarification
hmm,
regarding, I think, regarding the second question today, what we have solved.
okay,
See, the element which we can't find out using the dictator, we said
yeah,
that's boron. But in the lecture, somewhere we said that if the windowless dictators are used, then we can even extend the
yeah, yeah,
feasibility of dictating it to boron.
yeah,
So when such a kind of question comes, so that is also being explained in the lecture that we can
yeah,
identifying boron is also possible.
yeah, yeah, yeah.
So in such cases, how should we conclude the answer?
Yeah, so the thing is here, in question itself, it will be good that if they have given you the window that what it is made up of. So here, like element cannot, so like basically the EDS is known for, cannot detect the light element because the atomic number which is having a very less. So it is saying that by using like a polymer in the window, so that is possibility of the detection, but they cannot even assure. Even though if you can detect, but you cannot detect in a very exactly that what is the exact composition of that. Okay, so there also you will be not so much, you will not have a so much surety. Okay, so that is your correct, although it is saying that you can detect, but it will always be preferable that if you have a less element, then it will be difficult to detect by your this EDS. Okay,
So can I add one more along with this? I have a small doubt.
okay,
So if we want to detect such kind of elements which is having very low atomic number,
hmm.
then we have to go for wavelength spectroscopy. Am I right?
Wavelength spectroscopy.
Is it right? I'm not sure whether my statement is right or not.
uh,
So from
I
EDS we cannot identify these lighter elements that I understood. But if we want to detect something like that,
So
So what
actually,
should be?
I also do not think I'm also not sure that regarding your WDS that whether it can detect. I also have to find, and you also just see the lecture or search. But apart from this, the alternative that I can give is there are many different techniques also. You just cannot go with the ETS. If you want to find out the composition, the exact composition of your, this what to say of your specimen or your sample, you can there is many techniques even you can get regarding your oxidation state or not just elemental. So there are many techniques from where you can get your compositional details. Okay.
Okay, thank you. So the reason why I asked is that, see, I think I misjudged. In the wavelength dispersive spectroscopy, some wave broadening and all those things was explained. So
Okay.
I thought in the wavelength spectroscopy, sometimes these light elements may be detected. So that's the reason
Okay.
why I asked the question.
Yeah, yeah, it's fine. No, no, no,
Yeah.
no issue. So
Thank you.
yeah, yeah, yeah. Okay. Yeah. Do you have any other question? No. Okay. So thank you guys, thank you for joining.
Thank you.
Yeah.